let's do it.
So which problem is this?
211 from Jackson.
Ah, okay. Oh, the cylinder.
Okay, the review 1 through 6 right here is basically what we talked about in the last lecture, and this time we're going to talk about it again, but with more precision and more examples. The basic idea of using this global versus local symmetry to make a eigensolution that matches the whatever happens to the system to the parameters in a very precise way is really the important part of this, and we'll get to look at that, what I call an orthocomplete parameter analysis of a tunneling problem or a mechanical vibration, which is what we'll do in the next lectures. So we're going to go over again in very much detail the analysis of the simplest non-abelian group. In other words, this is a non-abelian analysis that is very tricky, and the D3 group is the smallest non-commutative group and perfect target for testing out new methods to solve quantum mechanical or classical problems that involve symmetry. So, I'm going to go very quickly through this and then come back with more detail on some of the items that are in the review, just each a couple of slides at the most. The derivation of these projectors that are two-index projectors, that's the important part of this, and the expansion of group elements in them is very important and also very revealing on how this global, local business works. So let's go ahead and look at the first thing. We have a couple of new references that TC has installed, and we're working entirely on the new machine, so we're hoping to be able to search those references in a good way. And that's one of the things that's missing from this whole electronic force that a book has. All books have indexes. Some of them are lousy, some of them are really good. It takes a lot of work to make an index. We have no index so far for this, but the electronics is going to let us have one. You just pick up any word you can think of, I guess, and even graphics eventually, and it'll go find examples in whatever search domain you ask it to. So this, I'm looking forward to this because that's one of the weak points of scholarship, is obtaining references, right? It used to be you go to the library and open up a scroll, right? It's very different now. So let's just go ahead here with a reminder, and I already have one slide up there that shows this. Today I would really like to show you in a very precise way, and we did see how to actually make operators that were for the same group that was a non-commutative group, but each of them commuted with each other. This is the key thing about this external or global symmetry operator, and this operator that it essentially does the same thing if you follow this equation, except for an inverse from the inside. And that we need to make this a little bit clearer. What is it that made that possible with that funny matrix set of local versus global? And I'm referring to this one, where take the group table and arrange it so that the inverses of the elements that we take in order, and we're going to hold that order throughout this lecture. 120 degrees squared, that's what R and R squared stand for, and then 180 degree rotations around three different trigonal axes. And little diagram here indicates where the states are after those operations, which are indicated by the lines that are axes of rotation for the last three elements, or the R here, or R squared, indicates where this would go under 120 degree, or minus 120 degree, which is really what this one is. But they're set up in such a way we always have units on the diagonal of the table. And then we use each of the positions of those elements in the table to put ones on a matrix that is otherwise all zero. So this table right here that has the inverses on the top, and this table right here that has the inverses on the side, are the two global, that's that one, and local groups, symmetry groups, that we're going to have fight with each other over the quantum mechanical solution to a Hamiltonian that uses each of the group elements here as a parameter in a Hamiltonian. So it's kind of amazing that all of these, who don't commute with each other essentially at all, and all of these, same thing, but every one of these commutes with every one of these. That's something I want you to see just in the mechanics of the matrix structure. It's sort of magic right now. I'm going to take the magic away. That's what science is about, right? Getting rid of the magic. But it is still magic after we get done with that, and very, very powerful. So since all of these matrices down here have the symmetry that is represented by this, we're allowed to make the Hamiltonian a linear combination of these elements, these matrices down here. And for each of the elements we have a little letter that represents the element, but it's just a parameter. In this case, 3 real parameters. In this case, 2 possibly complex parameters. And then, of course, the unit is just the thing that shifts the diagonal of the Hamiltonian. So the magic of this and how this turns into a really powerful formula for all possible situations that this particular tunneling system has. And you remember, we're using the group operator to indicate the states. We're using the group operator to indicate transformations of those states, and now we're using the group operators to indicate actual motion of something, say a tunneling wave function or a force transmitted by some spring system to label actual motion, physical connections in the system. Okay, now the first stage, and then the second stage, and then the third stage are something that I want to make as clear as possible today. We've already been through these 3 stages very quickly through the third one, so we're going to be spending most of our time on that one. But I want to review the very first stage, and that is reducing the D3 non-commutative algebra to a subalgebra which is not only commuting with itself but with everything else in the algebra. The all-commuting class projectors and characters and that sort of thing is an important beginning for any algebra, but a group in particular with its classes. And I think the mathematical term that's used for the algebra of the all-commuting operators is the Algebra Center. And this is an algebra. Once you take linear combinations of group operators, you aren't talking group theory anymore. That's algebraic or ring theory or something else as far as mathematicians are concerned. For physicists, just quantum mechanics. And this is a 6-dimensional algebra. There are 6 elements in the D3 algebra, but the center is a 3-dimensional. It takes up half of the algebra space and consists of sums of elements in each class. The class of the unit by itself, the class of 120 degree plus or minus operations. There are two guys in that class. And then there are those 380 degree rotations. And each of these algebraic elements are the sums of their respective classes. And the object of this was to turn these operators through, have an algebra that looks like this. It's very easily read off of the group table. The group table is non-commutative, but the algebra table is completely commutative. This is the same as that. This is the same as that. That and that are the same. So this thing commutes not only with everything in there, but with every individual element that's outside of the center. The other three dimensions that are non-commutative dimensions, so to speak. So the first stage of this development of the, for physics, of this symmetry is to find the projectors. The class projectors would be a possible name for that. The central projectors, these three guys live in this turquoise region. This is kind of like a swimming pool on an otherwise desolate geography, okay? And those people get to swim and commute, okay? Outside of these things, they don't commute with each other at all. But they do commute with everybody in there. That's the thing to remember that's really important for studying the spectra that comes from a symmetry like this. So when you get done making the projectors, and that was basically done right in these first steps right here. These are the projectors, very special linear combinations of these. But what's important to remember is that the coefficients of these, apart from a normalizing factor, 1, 1, 1, it's got a 1/6, and that's the top row of the character table. The next row in the character table, 1, 1, minus 1, is right here, and then 2, minus 1, 0 is the last one, and that's the representation that makes this symmetry work. That's the one that is two-dimensional. So this is the one that can split. This one will split depending on how you want to do it, but the way we did it was we took a particular element out of this outside of the center part of the group. One of the 180 degree rotations decided, you are the blessed element. We are going to make you diagonal. Okay, we're going to make you have a quantum number that means something if this is a quantum problem. So this subgroup has projectors that we know and love. Those projectors are 1 plus and 1 minus the two elements in there, and they're given names PA1 and PA2. Actually, P0 mod 2 and P1 mod 2. Those projectors, 1 plus I3, 1 minus I3, attach that to this projector of the center, and you get some things that don't commute anymore, but you split it. So the sum of this projector and this projector right here will have these sort of cumbersome notation associated with writing the name of the representation that split them, say 0, 2, twice as a subscript. And the same thing down here, the P1 modulo 2, the anti-symmetric projector of this C2 subgroup is given the name 1 modulo 2, but twice, and those twice are representing indices of what's going to be a matrix operator. That is the basic idea. So that's one way. There's just the character table is unique. You publish these numbers in books all over the world that anything to do with symmetry analysis, particularly in chemistry departments. There are a lot more of these books there than there are in the physics departments. But that actually shouldn't be. It should be the other way around. It just doesn't happen to be. The chemists make much more use of this stuff than physicists for the most part. And the idea that these are unique is in contrast to these projectors that we're making here, these big guys here that come tumbling out of the splitting process. So this particular splitting process has got a sort of a red color associated with it, because this is a splitting process that's going to give us standing waves. It's going to give us real solutions. And that's a more convenient thing to work with, so I think I kind of favor the red guys in this case. But that isn't the only way it splits. There's an infinite number of other ways, but they're the most opposite to this particular way is this green for go. And that means you're using a subgroup C3 with its projectors. It has 3 projectors, but only 2 of them are relevant, and it splits this projector here, PE, the bottom row here, the 2-dimensional projector. It splits it in 2, but a very different 2. And these coefficients here are all e to the 2 pi I 3, or its inverse, conjugate, whatever you want to call it. So these numbers here are definitely complex. But still, you sum this one up, you get your all commuting projector back again. Okay, so it's handling these things with the double indices that's going to be the tough thing today, and the one thing we glossed over in the last lecture. So we're going to really bury our noses in what those 2 indices can do, because they are local and global indices. That's what they really come down to, and we're going to make that as clear as we can. Even clearer than it was in the last lecture, which may not have been very clear, but I want to make a better try at it today.
Dr. Harvey?
Yes.
You said the red bar makes standing waves?
Let me back up here. The red part here consists of the projector operators that we're eventually going to label them X, X, and Y, Y. But right now we're labeling 1 mod 2 and 0 mod 2 are the other way around. So these guys right here, by making waves that point in the X direction or in the Y direction, kind of like orbitals in a chemistry book, right? These guys are real. They're standing waves. Whereas the projectors that you make out of there, that 1, 1 and that 2, 2, that's 1, 1 and 2, 2 mod 3, whole different story. That's something that's been split by these projectors of the C3 group, and they give us something that looks pretty much like that. So I don't know if your question was about, what's the mathematical difference. That's complex, but the physics difference is, I think, the most important.
What is the physics difference again? That you can make galloping waves?
As soon as you get a complex number in a wave function, the phases are different, okay? If you have real numbers, then the phases are either in phase or out of phase. You got plus and minus 1, that's all you can work with, right? Or plus and minus some number, but still that plus and minus is going to decide where those the phases are. Now, as soon as you have phase out of phase, right, something's giving energy to somebody else. The one that's leading is giving energy to the one that's following. Or giving something. It could be just more sugar. I mean, something is being transferred. And that's what complex numbers do. So, green for go, these are current carrying. These are standing, they just sit there and go up and down, right? So that's what this choice of splitting amounts to when you have a stark comparison of split. Because I can split this thing using virtually, I would say, a triple infinity of possibilities, you say. These are just extremes, 2 extremes of the splitting. Okay? Well, we're going to just work with the red one today. But it isn't, after you get all done, you don't have to start over. You can make your change at the end. And that's very easy to do that, because now you know the physics. So, check on that later. Now this is something I just breezed over really, I would say fairly quickly. And the idea is that G is equal to the unit times G times the unit, and each unit here is a sum of irreducible projection operators. Now these two right here that are labeled A1 and A2, they were irreducible even before we tried splitting, because they don't split. We saw that by some character analysis, and we'll see it other ways today. But these two guys right here that came splitting out, the X and the Y, they are idempotent. They're orthogonal to each other and to everybody else in this set here. But these are the ones that are up for grabs. These could have easily been complex projectors made by C3. In any case, that's our completeness relation for irreducible projectors. These sum up to 1. And there it is again. There's 1 again. Okay. So now it looks like with 4 of these things here, I'm going to get 4 times 4 things that I have to worry about. But that's not what happens, because these two don't give you but 1 each. These two, 2 times 2 is 4, gives me 4 terms. And some of these terms are not idempotent. Some of them are nilpotent. So that's what we're going to have to deal with right away at the beginning here, is to make it clear how you get those nilpotents. These things that have different indices associated with them. Those that are placeholders for irreducible representation components that are off diagonal, either the upper right-hand corner or the lower left-hand corner for those two right there respectively. So that's what we have to deal with. Now a key projector identity is this one, and we'll be showing that in a number of different ways. But the basic idea is that when you have all these projectors here going together to make sandwiches, with this in the peanut butter place and these are the breads around it, they reduce to this thing right here, which is one of those either idempotent if these are equal, or nilpotent if they're not equal, multiplied by a coefficient that we're after. That's the irreducible representation of this particular, that goes with this particular projector of type alpha, say E, and that's the only one that we're really worried about, because it's the only one that gives us 4 things as opposed to 1 each for the scalar and the pseudoscalar. This is the vector representation, another point we're going to make later on. Okay, so this is a review. This is now talking about the third stage. This is the last part of our review, and it goes on and on, okay? Because this is the one that gives these numbers, these matrices with these numbers, and the identity there is something that I kind of left out in the last lecture, but now we're really going to have to deal with that in a very way. So we're going to get down and dirty, and we're going to get some matrices and just go through and by brute force with what we know about these quantities, derive their numerical values. And then we'll use them for global versus local and all of that stuff, and get some better idea of what that amounts to. But here is a typical projector that came out of the splitting. So here are the 2 index projectors that were split from the class. The all-commuting PE has split into this plus this, into this plus this. Okay, that's what it split to. You add them back up again, and you get our old friend at the bottom of the character table. Okay, but this is a full-blown irreducible. You can't split this guy anymore. Any matrix you make of it will have a trace of 1, which means it can't split. Whereas this guy right here that split, it has a trace of 2 in any sort of a matrix that would be inquiring on how it is, or if it was going to split. So the idea here is to go ahead and use our 00 mod 2 projector, this guy right here. Okay, so this is the way we wrote it when we split it, but now that we realize there's a bigger world waiting for us, this is the way we write. And we write all of our projectors, even the ones that don't split, with a double index. And the reason for that is that you have to tell me both the global symmetry, which is the left number, and the local symmetry, which is the right number, the right-hand number. So we looked a little bit at that. We're going to be looking more at that in just a few minutes here. But here is where we get one of these irreducible representation components. The 120-degree operator has a 0202 component. It's a diagonal component, a little 2x2 matrix that we need to calculate, and this would give it to us very nicely. I just ask, what is the matrix element that I would get by using these projectors in the full group space, which is 6-dimensional. So here it is with 2, -1, -1, -1, -1, 2. Okay, so that's what I'm going to do. I'm going to put one of those on this side, and then I'm going to take the matrix that goes with 120 degrees. I'm sorry, the matrix goes with the operation 120 degrees. Okay, and let's go ahead on this slide over here just to get to the point where we actually have the matrices that we're going to be looking at here. And we're going to be using a global operator, so we'll use the top one. And there, right here, is that matrix that is sitting there. So the thing is called r to the first power. That's this guy right here. This is the matrix for it. Now this letter R here stands for something that's very old in group theory. R stands for regular. This is called the regular representation because it does a regular permutation, and a regular permutation is defined as one that moves everything. I don't know why. If it was irregular, I mean, is that because it can't find all of the things it's going to move? I don't know. But anyway, that R is something that's very old, and you'll see that in a lot of different descriptions of the group thing. That's what we're using, okay? And I'm going to normalize these guys. They're both normalized by the square root of 12. That's 2 times the square root of 3. They're both normalized by that, okay? So when I put those numbers in and go ahead and work this matrix on there, and it regularly permutes all of these numbers into that, then I take the scalar product, which is this, and I get -1/2. Okay, that's a big deal. That's the -1/2 that you see on the diagonal of this particular little 2x2 irreducible representation that we're going to make. Now let's go try it and see if we can get an off-diagonal thing. This is a complete garbage way to do it because I'm not respecting local global. I'm not doing anything right. I get what I deserve. 0. Okay, this is not the way to do it, but just in case you someday think you might want to try getting it this way, there are reasons which we'll see later on why that has to give you 0. You can't change 2 local indices at the same time with one operator. Okay, so we have to figure out how to drive the darn thing. Okay, so here's what we do. And this is, as I say, the brute force method for getting a projector, an irreducible projector that is a nilpotent operator, not an idempotent. And all of the other cases, we use the same projector on both sides of an element, and we get an idempotent times an irreducible representation component. Now we're going to get an off-diagonal component by using different projectors here. And you say, well, why did I just put a 1 here? Why do I could just get the projector, couldn't I? No way. Those things are orthogonal to that thing. That's what gave me the 0. I got to put a real element in there that keeps me from getting 0. And gives me an actual number at this point right here that's not 0. Okay? So that's what we're after. This is the view of taking all of these elements here and their coefficients and multiplying it by their... So I basically just plunk the group table down here, you see. Now, I'm trying to calculate this thing, so I work this thing out and lay it on the top here. So here's R1 times the projector, okay, and we already saw what that did. That just multiplies everything in there by R1, the unit gets a, that had a 2 times, gets 2 times R1 and so forth. And then I just reorder them so they're in the canonical order. Then remember the top had R squared here, and then R1, and then I1, I2, and I3, with the numbers that go right here. For example, -2 was down at the end here, now ends up there. So I just have to go through and multiply all these numbers by all these numbers to get here a huge combination of 6 things, right? You have to write that out and see what that gives. And it turns out it gives me nothing for the unit. It gives me nothing for I3. Those are the 2 guys that were going to be diagonal in our system that we're working on here. And I get 9 each with plus or minus signs of the others, the other 4. Okay, and it's divided by 36, which is the multiple of this is 1/6 right here, and this one has also got a 1/6. So it's 1 over 36 times those, and that's these guys right here. And the transpose of this, which will get me the other side of the story, has to do this. When you do a transpose, which is equivalent to doing an inverse for unitary operators, but it gives you these guys flipped over. Okay, the B still in the pickle, but the A and C switch positions. Okay, so that's what went on here. All that happened was these 2 guys switched their plus and minus signs. These guys, the transpose of them is themselves, so they didn't get changed. Okay? So these are 2 nilpotent or nilpotent or something. Nihilistic? I don't know what adjectives you want to use for these guys. But what I want to do is I want to take a product of them. And the reason for that is I want to figure out what it is, what operator did I produce in doing this. This is going to let me actually calculate the matrix element that goes with this particular 0 to 1, 2, that's x, y component of the D matrices that we're after here. Okay, so that's the deal. And when you do this product right here, okay, you have to be aware that this is an idempotent right here, okay, and the PE11 just gives me a P1, which PE1, and the R1 and the R2 then get to see each other, and the R1 and R2 are inverse to each other, so I get a 1. So this thing, this product right here is an idempotent we've already seen. We called it 0, 2. It's one of the ones that split out. Actually, you have 2 indices down there, and then the reason for I have 2 indices is because here are 2 indices, you see. And this thing is mirroring that thing as an idempotent. So the idea is to match that with what we got up here. And this is just the definitions of some of the other diodes. Okay? So what we do is we take these count these guys out because we had 0, and I multiply them together to get this thing. Okay? And that thing is indeed the idempotent that split out. This is the original projector down here, the irreducible projector associated with 0 mod 2, and that's what we're getting, supposedly, times some constant, which we're very interested in. We're interested in this guy, and we're interested in comparing that with the original, which is 1/6. We got 1/8 from this one. The 16th 4, blah, 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 came out to that. Okay? So, we want to connect those 2. Basically what we're doing, you see, when you put this thing together is each of these coefficients come in. This is a complex quantity of 1 R1 and then the R1. It gives me an absolute square number right here. Okay? And I'm going to calculate that absolute square by solving for it by just simply taking a ratio of this coefficient with the original one that goes with this idempotent. So I get 1/8 over 1/6. That's 3/4. Bingo. The only trouble is plus or minus. It's ambiguous. So it's very powerful in a sense, but it's very weak in terms of determining the actual phase. So what are we going to do? Well, this is where you actually use the projectors as bases and see what you get by doing a single operation on one of these or its transpose. So either use this guy or its transpose. There they are. There's the product that goes on the top, and there's the product that goes on the side that made this. We covered our P02 projector, and now we have to figure out, argue about the coefficient. That coefficient ratio is the square of the number we're after.
Dr. Harter?
Yeah.
So, right below that big table, you
This
said
is this
that,
guy right here.
that's a nilpotent like those two operators, like,
These are projectors. These are idempotents. Both of these are idempotents.
Okay,
Which just
yeah.
give PE1, which then commutes with R1. Give us a unit in the middle there, and
Okay.
then these two come up, and they finally end up producing the projector times some number. Okay. Each of these guys that we have here has, by that identity, be the number we're after times this nilpotent projector, and this one's the same thing.
does that nilpotent projector commutes with DE 1 mode 2, 0 mode 2?
It will be very close. It'll produce this. And the other one, which when you flip it, all it does is switch the signs on these two guys, which are transposes of each other, and leaves these alone.
Okay.
So that thing right there, you square, you get you get the projection operator if you put this with this. But if you square this with itself, 0. Square this one with itself, 0.
They are nilpotent themselves, right?
Yeah. And you can see why that would be. If I put this guy next to himself, the 0, 2 is going to run into 1, 2, right? 0 right away, and it's a single factor, so it's dead. Okay, so those guys with unequal indices, just the opposite of idempotence.
Yeah, because I mean that makes sense because that projector is in sort of a sense is
Yeah.
orthogonal to the P1
Yeah.
mode 2, right?
Yep, yep. You would be making vectors that are orthogonal if you applied it to
I mean, if I think about it in terms of
Yeah.
like a vector representation, like their vector representation.
And that's what we're doing here, right?
Okay.
Yeah. Now, an easy way, and this I bring back, this is the what we call the bottom-up way of doing things, okay? Supposedly the elegant way to do the things, but it's a lot of work. If we did the octahedral group of this thing, we got a matrix that would take up the whole wall. And we have to multiply it, right? So, I think the way we did it the first time is only one class, as opposed to we'd stay here until summer was half done. Okay, so let's do it the top-down way. We know this thing's a vector, okay? In fact, those are the modes that we would be dealing with, and will be dealing with at the end of today and a good part of the next lecture. But in this case, what I'm doing here is just looking once again at the split-off projector here, and then the transpose here. This is the split-off projector that gives this vector, that's this one, and then this is the projector that gives me a vector that looks like that, and then I'm putting an R1 between them, okay? And that's the thing that's producing, once I've seen what I did, that's the thing that's producing here a square root of 3 over 2 with the sign, you see. But we could do this very easily. As I pointed out, all of that top-down was, I know that this is a vector. Let me put a vector here and rotate it by 120 degrees, and what am I going to get? I'm going to get a minus a half here, that's the cosine of 120, and I'm going to get a plus the square root of 3 right there, that's the sine of 120, and that's exactly what the doctor ordered right here if you were just going to multiply the unit x vector, this thing. So, child's play, right? When you come from the top down and you know it's a vector's representation, that's all there is to it. Now, this is a little hard to read. this is a particular mode that we call the X mode, and it kind of looks like that. It only moves in the X. These two cancel each other. We'll be getting that from our irreducible projectors. And I turn it by 120 degrees, so now it's doing that. That's equivalent to a vector in that direction. And then I say, what is this thing in terms of the two X? And now here's the Y mode. This is a Y mode where the X cancels out, and this thing is going like this, essentially. Okay, so that's a coefficient that I would be getting as I multiplied this thing by 1 right here, and then the minus a half is what I'm getting when this thing multiplies by 1. Okay? So this is just child's play, you see. This is what you would try to do when you have a really big group like our icosahedral group. You try to sneak in on it. Trying to go bottom up very often leads to a lot of work that you really would end up putting in mathematics or something like that. But you often like to do things lots of different ways so you can check yourself. Because when you're out in the jungle with a big molecule, you want to have come there with a lot of different ways to check out yourself. Okay, so it's now time to make a comparison between the basis that you get just using group operators or the basis that you get after you've used the full set of projectors that we got by doing all of our algebra correctly. So that's what we're after. So we're going to be comparing the G basis, that's a little g for group element basis, which is giving us matrices that look like that, with some very much closer to the diagonal representations in this basis. And this basis has an algebra as opposed to this one, which has a group, but this one has a group algebra, that one does too. So we just got through using this group table versus this group table. Here's the one that gives us the global. This is the one that's giving us the local matrices for each group element. What about something that gives us the matrices for a projector? You see, this is the thing that we have right there. That's just the global part of it, and there's the local part right there. So it's just a copy of that particular thing. Now we're going to take the projectors into account. Okay? And here's their multiplication tables. And now this multiplication table right here is giving us this very fancy multiplication, which should essentially be obvious now, because we know that these A's and B and the C and the D represent projectors that are sort of guarding some group element. The B projector is on the right-hand side, the A projector is on the left-hand side. And so the B projector here is going to run smack dab, and the ones on the right side is going to run smack dab into the projector C that's living on the left side of this projector inside there. That's the, remember, that's how these things are made. And then the D projector is sort of out to the side there, not pretty safe from getting hit by B. But when B and C hit each other, if B and C are not equal, this is dead duck. So delta function 0 if B and C are not equal, it's 1 if they are. And then you're going to end up with a projector that has some stuff in the middle, but it's A and D, so you're going to end up with a projector AD when you do that. So for example, PXX times PYX is nothing. Times PYY is nothing. It's got a Y on the left side. But PXX times PXX, well, we know what the answer to that is. It's PXX. It's idempotent. But PXX times this nilpotent is that nilpotent. The PXX just gets absorbed by the PX that's hiding inside that projector and gives you this component. So this is what is called a simple matrix algebra by mathematicians. Is that pretty clear? And there's its table. And just like this group table tells you where the matrix elements are by putting 1 for each, so does that one. But that's just the global part. This is the local part down here. And just like I switched these with their transposes, every one of them, but there was only 2 pairs that were transposes, transposable. This one only has 2 projectors that are transposable. The rest of them are all diagonal. Yx flipped with xy gives me a whole new table that looks like this. And you'll notice that they're all the same within each of these blocks. 2 things the same, 2 things the same, 2 things the same. It's quite a difference from this. These don't change. They don't care. That's abelian stuff. We don't have global local to worry about with abelian algebras, but this one is not abelian, so more than half of its representation is taken up by issues having to do with commutativity. Okay, so we're going to make use of these 2. Okay? First, let's do this one. And that's what you should think about these projectors as, just like you think about the group operators this way. These are placeholders for the actual coefficients that are the irreducible representations of numbers that we know and love for physics. Okay? So each of these matrices that represents Pxx, for example, okay? Well, Pxx has a 1 right there. Okay? Oh, but Pxx shows up down here, so I have another 1 right there. But everything else is 0. This is even simpler than the regular representation, which had 6 1s in every one of them, right? None of these has anything more than a couple of 1s. And these 2, they have to get along with just a 1 that goes with their particular block. And that's abelian stuff. But this is a whole different ballgame. Okay? So, the Pxy and Yx, I don't know what happened there, somebody got covered up there. But we'll look at this one because these are identical. These 2 are identical. Yx, okay? There's Yx. There's the 1. There's where Yx is in this multiplication table. So that's the whole idea of writing a reduced representation. And here are the coefficients that would go with that. This xx, xy, yx, and yy sits there in the placeholders that are produced by, respectively, xx, xy, yx, and yy. And that happens twice, because this representation gets to appear twice in the regular representation. Exactly the number of its dimension, and that's a very important thing. Here's the other way to look at it, local. This is the local matrix that you would get. And it's very different. It's got a lot of zeros in each of the little blocks there. But still, it produces, for example, for Pxx, 1, 1 right there. It's got 2 1s that match the element, just like we do. And all we did, these 2 blue arrows indicate that we switched those 2 guys. That's all we did. We did a transpose of every element. They were the only ones that actually transposed. Okay? Pretty good? And there they are together. Now's when you get to see why it is that everything you make in the local department commutes with everything that you make in the global department. This is where you get to see that. Because look what's happening here. When I take a matrix that has the blocks filled up, A, B, C, D, like this one does here, okay? A, B, C, D, okay? These guys right here are a little bit different, you see. These are the global guys, and they fill up the blocks on the diagonal. These guys make use of the stuff that's off diagonal. They always do it with a unit operator, right? Here this guy has 2 1s. Here the 2 1s are together. This guy's got 2 1s off in the corner. These guys got a unit matrix up here, right? So, here I go A, B, C, D, and then I go A, B, C, D in a block. This one goes A, B, A, B, B, C, C, D, D, okay? Okay, it's pretty obvious, if you just look at the matrix multiplication, that this commutes with this. That is, these are equal. This one comes second after this one. Here it's second after the black one. Okay? Multiply them together. Well, if the little a and the little big A didn't commute, we'd be in trouble because this one is little a times big A and this one's big A times little a, but these are numbers. Does that make sense? That's what this gives you. That's why, sometimes I think this actually has a name. It's called an intertwining algebra. And this is how they intertwine. That's a big name for something that's pretty simple. But it's prosaic. They are intertwined. Literally, right? They stay out of each other's way while they're intertwined. How do you do that? That's not been worked out. You'd have to read the advanced version of the Kama Sutra to figure that one out. There it is. Okay. Sex sells, right? All right. Now, we've got to talk about the hardware of those operators. And this is going to apply both to global and local, but it will, I think, make some sense. So we're back doing what we've already talked about a lot, except now I'm not going to use 0 mod 2 twice. That I'm just going to write XX. And then 0 mod 2, 1 mod 2, I'm going to write that XY, and so forth. So from now on, I'm pretty much going to use that because we're done with the algebra that did the splitting. So now it's just a matter of dealing with these 6 things here, these 6 terms. These are the things we got by doing G equals 1 times G times 1 trick. And the irreducible class idempotents, they deserve to have whatever sub-indices they deserve. Now A1 goes very nicely with 0 mod 2 or the X symmetry. The pseudo-scalar goes very much with the Y. So now that we realize that everything that we do should have a global and a local labeling, it makes sense to keep a double level for something that is just one-dimensional. But we certainly need it over there because that's a 2x2 matrix, and we are actually getting 2 of those to appear in the regular representation, as we've already seen. So there are the identities that take the situation that happens when 1 times G times 1 is carried out, and you're making a whole bunch of the group operator with 2 projectors on either side. And since these projectors from the A1 and A2 pseudoscalars are all commuting projectors, they're part of the class algebra. They did not split. Splitting makes the PEXX not commute with that operator. And so just to bring that point up, I cannot, when I write a nilpotent operator, as they say, the split idempotents, those indices are really essential. They're optional up there until we actually do that. Now, besides the 4 idempotent projectors you see, we've got 2 nilpotent projectors. Okay, things that square to 0. These square to themselves, and a sum of them squares to something that's all commuting, and all commuting idempotent. Anyway, the orthogonality of projectors, ordinary kinds, is being generalized here, and we've already mentioned this, but that's the basic idea of these 2 indices, why they're so crucial, and we're making these new kinds of things that are some nilpotent, some idempotent. In this case, we only got 2 of these, okay, but 4 of these, but really we only have 2 diagonal ones, so they're kind of on an equal footing. But be aware that as you do bigger and bigger symmetries, whose population is going to be the biggest? Is it going to be the idempotents, or is it going to be the nilpotents? And you got to remember, the idempotents have to live on a diagonal, and in a great big matrix, that's a very small part of the whole field, right?
Nilpotent population will be bigger.
It's an n squared compared to an n, right, basically. Okay, so that is, with that said, we think that we're working with a pretty small group here, so we only have the two off-diagonal and the two diagonal things. Then these two guys who stay on the diagonal. So there's the placeholder matrix that works for global symmetry. Now, we're not going to change the numbers that are in those representations anywhere in this lecture, so we've only derived this one, and then by trace formula you can see that that one had to be there as well, and then we derived this guy right here, and then again, just a simple algebra would show the transpose of this has to be that, and so forth. Then it's up to you to get these two. These are given when we did the splitting of I3 into symmetric and antisymmetric. Those numbers were set. Okay, and it's the only diagonal matrix in the whole thing besides the unit. Okay, so let's take a look here. We got left transformations and we've got right transformations. So when I hit the thing from this side, I get something that's a little bit different, but very similar to what I hit it from this side. Okay, and that's what makes the global local algebra important. So if I apply a G here, and the G is a linear combination of all of the projectors, nilpotent and otherwise. These guys nilpotent if the numbers are not the same. And there's the algebra right there, written out in fancy ways. First of all, a representation A1 has nothing to do with an E, so that delta function is going to kill most of the elements, and then it's just a question of these two indices right here that are sandwiched, are running into each other to decide whether it's going to be 0 or 1. And finally, you get a very simple result in either case. Okay. So when I do a G, which is a linear combination of all these projectors, this is going to run into that. So I'm going to immediately get an n prime m delta function right here to kill this thing if those two are not equal. And then what I'll be left with after I've done that is the outside index, m prime n, will go right here. So this is showing us right off the bat what effect G has on one of these projectors, these irreducible projectors. It produces a combination over n prime of the irreducible matrix. So there's the left-hand transformation that you would get in any group theory book. This would be, a given. But here we're deriving, you see. That's important. We're trying to keep the logic as tight and clear as possible. Okay. So this is a left action transfer of a ket. Now we're talking about rotor kets here if we're doing the molecular physics. So we're already talking about lab, that's the global, and body, that's the local. Okay, so this is where we're actually manipulating them with transformations, not just operators that give eigenvalues. But that's contained in this result right here. This is using Dirac notation to make the expression. This is probably the most revealing expression of what's going on here. If you've got a global, it only works with the m's, and it gives you the irreducible representation that is exactly those m's, m prime, m. And if you don't keep the n's the same, that's 0. That zeroes it. And that's the 0 that we got, that I growled at when we were trying to cheat to get the off-diagonal thing. Doesn't work. I have to use a more laborious approach. Now, this requires some normalization. So when you put this thing ket to bra, you get this thing right here, and it boils down to a projection operator that may be a nilpotent if the n primes are not equal. In other words, if n prime is not equal, like I said, goodbye. This thing has no diagonal elements, so it's asking for the 1, 1 diagonal, and that is not going to be anything but 0. So there's sort of a double index relationship if you do a scalar product with this. This has to be equal to that, this has to be equal to that, this has to be equal to that, n prime has to be equal to n. Okay, so 3 deltas for the scalar product. Okay, now the norm squared is the matrix element of that thing. We got to work that out. That'll come later in a few pages here. But let's just do the right-hand side to see what the deal is. Same deal, okay? Now we're talking about, when we talk about projectors, when we think of ket bras with different numbers in them, that's really kind of what we're doing with, at least in each of the mu subspaces, each of the irreducible subspaces. So we've only got one of those, that's the E, so we're talking about the E of D3 when we write these general results right here. So what you can do is you can just take this result right here and dagger it, okay? That gives me this result here, turned around and daggered. And this thing the same way, okay? Now the projectors dagger into a flip of M and N. There's no funny business there. That can be seen fairly easily. I think I'll be showing that obliquely later on. But there's the right and left thing now. So now when we apply the operator from that side, because the M's here are where they are, and this is G dagger now, what we'll find is that we'll get M prime M of G dagger. Well, that's not too different from what we've got over there. Okay, so at this point, it's a mute, sort of a moot thing, but I just wanted to make sure you see the right hand. Now we're going to do something with the right hand transformation in just a minute. But remember, if this matrix is unitary in almost all physics applications of symmetry in the area that we're kind of working in, they're all unitary. So what you get by doing this is a complex conjugate of a representation. M, M prime, okay? But you get the flip of M prime and M if you wanted to keep writing the G dagger. So this is all very persnickety sort of making sure that we've got our ducks in a row, so to speak.
Dr. Harter,
We use those manipulations so often.
can you go back?
Yes.
There. 1, 2, the second line.
That guy?
Yeah, that guy. What you're using? Up, 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 up,
Oh, here.
up. Yeah, down.
Down.
Yeah, there.
Yeah.
What is the purpose of using the contravariant notation with those mu's in that delta? Sorry, covariant, contravariant, I don't remember, but they are something like that.
Yeah, this very different from saying I have a vector with a contravariant, right, to sort up, and covariant, right? Very different. What we're going to do with altitude of indices is the ones that are highest represent a label of the highest symmetry we're working with. Okay? In this case, it would be mu equal to A1 or A2 or E, right?
Those are global symmetries, right?
Well, it could be local or global, right? But because remember, we've got a D3 that works in the global, and we got another D3 that commutes with that one that works in the local, right? So it could be either.
Okay.
But the high altitude indicates highness of the symmetry. Then the indices M and M, you know, they were just X and Y in our case, right? If we did our diagonalization and splitting to get X and Y. Otherwise it would be 0 mod 1 mod 3 and 2 mod 3. Those would be the two indices, right? We lose the 0 mod 3, remember? You only can get 2. The projector had 3 things, but one of them died on the way to the hospital, right? So, you know, that happens. It's a tragic business we work in here. Lots of daggers. Lots of nilpotents that are killing people. Yeah, it's really pretty bad. All right, let's see if we can get some life out of this. One of the things that we need to do is invert this expansion. I mean, this expansion is pretty obvious, written as a G with a 1 on either side, right? And the 1, you know, has its expansion, and the other one has it, and then they come together and they fight over what's in the middle and give us this. But how do I get the opposite? This is a case of making a local state, right? That is, if I'm talking about a wave function over all possible m's and n primes and all of that, I've got a lot of beating going on, right? That's going to be like a coherent state, and it probably won't be coherent. Okay? So we really would like to get back to the point where we write just the p as a function of g, because then we're going to be getting a wave function over all of the positions described by g. But because of the nature of this, it's not trivial. There's going to be some real estate here that's needed to prove this. Okay? But I claim it's better than what you'll find in most of the text to try to avoid this question altogether. Anyway, we consider left action by some operator. It doesn't necessarily have to be a group operator. It could be an algebraic operator. But in this case, let's just imagine it is a group operator hitting there, and it's going to do the thing. And the purpose of this will be to get this coefficient, because we already know kind of what F does to G in terms of the representations of this group thing. So, what I have put here is I'm just going here and I'm saying I would like this is an F times G, so I'm going to be letting F times G be equal to H, and if I do that, then G has to be F inverse H. So I'm going to replace this thing as a coefficient that's over all G, but that means it's going to be over F inverse all H. Now that's the trick you do very often in the group theory to make answers come out. So this is nothing that I would claim is so very special. Now, the trace of the regular representation, let's look at the regular representation again. And do you see a trace in any of these matrices? Except this one. Right? No trace. Right? You can't. It's a regular representation. It moved everything. If it had left something alone, it would be on the diagonal, and we'd have a trace. Okay? So this is a really key thing to remember about a regular representation. 0 everywhere, except for the unit operator. And then all of a sudden, you get the full order of the group, which is 6 here. Okay? So that's a coefficient that we're going to have in this thing we're trying to derive. Okay? So the trace of this thing, okay, is the sum over H, and we're just going to be taking the trace of this operator. This is a coefficient that I'll put here. Okay? So this is a sum between H and the order of the group, so you can kind of see where we're going with that. Okay, so that results in not a sum, but just one term. The element that has all of the trace is this one. Okay, and it's a number that's equal to the order. So that's kind of neat, because at this point we have a formula, sort of, for the coefficient that we're trying to derive. Okay, it's 1 over G times that thing. Oh gosh, what are we going to do with that? Okay, so we've got to actually put the elements in there. Now the trace of the regular representation of the projectors, and here they are, it is 1 for this, 1 for this, but 2 for this one, because there's 2 representations of the E-type. Okay? It's 0 for that guy. Nilpotents have no trace. They stay away from the diagonal. So is this a nilpotent. No deal there. But this one, same thing. Both these and these get a trace of 2, which is, coincidentally, because of the way this is built, the dimension of that irreducible representation. The dimension L equal 2 for mu equal E. Now that's going to work for the diagonal ones. It's 0 any other case. All right? So we can solve there. That's the trace of the projection operator in a regular representation. It's 0 if it's a nilpotent. You got to have m equal to n, so it's an idempotent. And then it's equal to the dimension of that representation mu. So this is going to work for all icosahedral, octahedral, everything. This is a golden for all finite groups. So you got to solve this relationship here for this coefficient. And there you go. It's going to be the trace of this. Okay, so that means we got to go through and write down what the trace is of that with this darn F inverse there. Okay, well, we know how left action occurs. Left action occurs with the D's. Okay, summing over of the left index, M prime. Okay, so we're going to have a coefficient. It's going to be a irreducible representation of this operator F with an inverse on it. Okay, so there you go. You get a trace over this, the D of this. Okay, and that's a pretty nice formula already because we know what the trace of that guy is. Mostly 0, but there'll be a dimension associated with when it's not 0. Okay, so the trace of regular representation of that is just a couple of delta functions. Well, that's going to simplify our sum here a little bit. Okay, it's going to give us a coefficient of single term nm, that's what the delta's told us, of F inverse, and then this ratio. Now what's interesting is the dimension, and this is something I ask you see if you can find a proof for this. This dimension also divides the order of the group. Remember, order of the class divides the group, order of subgroups all divide the order of the group. So does the dimension of the irreducible representation. That's a very high level case of a perfect division. So see if you can come up with a proof of that. I know of one, but it's pretty crazy. Anyway.
Can you repeat that? I would like to solve that problem.
This is an inverse integer. GO, order group, in this case 6, divided by 2 is an integer. 6 divided by 2 is 3 for our group. On the E, it's 6 for all the others, right? Because this is 1. See if you can get a classy proof of that. That is really, I think, one of the more beautiful things. Anyway, here's our result. We now have a projection operator written as a linear combination of group operators. So this is the wave function, you might say, of a particular wave that has a certain amplitude. This is the amplitude, but it's got to take that into account on each of the G's positions. Okay? If it's unitary, it's very simple. It isn't that different from this. It's just turned around, right? It's a linear combination of the star of D. And that's why we always use the star of D to get the wave functions. Remember when we were doing the top-down approach and the D's were coming from the R3 angular momentum matrices? We always used the star to write our wave function. But that goes back to our CN analysis. If you go back and look at that, same thing. The character tables are not the wave function, but wave function star traditionally. Yes?
One question. There, so that L mu.
Dimension of irreducible.
So mu is the dimension, or L mu is the dimension?
L and then labeled by mu. I don't like to write L to the mu's power, because that's not what I mean, right?
Okay.
It's just a label of the letter L that's very traditionally used to give you dimension. For example, if this was an L parentheses J, we've been looking at, that was 2J plus 1, right?
Yeah.
That was the angular momentum, a triplet for J equal 1, right? And then a pentuplet, whatever that is, a handshake for angular momentum 2, right? And then there, of course, was the angular momentum 3 halves, right? So that number appeared in our projection that we wrote, right? But the projection was just kind of a nebulous thing. Here it's it's blood and soil, so to speak. I don't like to use that terminology, but that is a really powerful formula right there.
Yeah, but you asked a question about like the proof. I forgot because I was thinking in something else. Can you ask the question again?
GO, order group,
Uh-huh.
divided by any dimension of an irreducible representation of that group is an integer. L evenly divides the order. Just like subgroup order, class order, right? Pick any class, it's got to divide the order of the group. Pick any subgroup, got to divide the order of the group. That was a Lagrange, right? This is super Lagrange.
The dimension of that thing.
Irreducible representations, right? Now remember, the sum of the dimensions is the rank, the number of mutually commuting observables. It's a very physical thing, it's very important.
The number
Right.
of mutually commuting observables.
And that's a key number in any sort of high-level quantum mechanics. Okay, it's how many observables do I have? I'm really limited by the uncertainty principle, but I've got these precious observables. Hey, every one of them I love, right? I've got to know the number of them, right? Well, for a D3, the rank, the sum of A1, that's 1, plus A2's dimension, that's 1, and then E's dimension is 2, so 1 plus 1 plus 2, that's 4. That's the rank 4 of the group we're working with here. It has that number of mutually observable quantities.
And the dimension of that one was 2, right?
The dimension of
Of what you just said. You said like 2 plus 1 plus 1.
the dimension of the irreducible representation of D3 is 2. Okay, and it divides the order of the group very nicely because it's an even order. Yeah.
That's
See,
a
these
pretty-
L's don't get very big. Even for the icosahedral group, the biggest one's 5.
So that means I mean, if what you said, that means that that's a fractional number, right?
Well, it's an inverse integer. Yeah,
Yeah.
yeah. But OG over L, that's always an integer.
Oh.
Okay.
That's
Yeah. It kind of, it's funny to say, it makes an inverse integer, right?
Have you proved it?
Which is, you know,
Did you
A
turn
decimal.
the D4?
D4.
Did
Yeah.
you turn
No,
to
no,
that?
no, no.
Oh, I thought if you had, you could.
That's a good one to look at. Actually, if you really want to get up on the icosahedron someday, you might want to try D5. D5's full of golden ratios, all kinds of weird stuff. So, you know, if you're equipped to handle lots of square roots of 5 and things like that, I recommend D5. But if you're just new at this game, take D4 first. Yeah. Okay. Anything else for this? This is getting close to the end of the secretarial work, but this really important secretarial work. Because, you know, it's following these rules carefully keeps you from wasting time. And it's really easy to waste time with stuff like this because you made some little tiny goof along the way. This is like programming.
I'll second that.
Okay, here we go. Hamiltonian, okay, is going to be written as linear combinations of things that are like what we're talking about here. But basic idea is for the unitary thing, we can write a projection operator with the indices in the same order they come here. In other words, that's the wave function right there, to be at position G in this state here, which for our R3 was J, M, N. And by M and N, we meant the laboratory M that everyone's used to, and then this bizarre, crazy internal N that only a few molecular physicists seem to be conversant in. And I would count amongst that the nuclear physicists. Okay? So that state has this as its wave function, with the L over O of G in the case of a discrete one. We didn't have that problem with the R3 because the O of G is infinite, right? It became a question of how do you integrate it, what are the weight function that you use for Euler angles or axis angles. Okay, so what we need here is the norm that goes with that. We have already worked that out, but whatever that norm is, it will be in the denominator of the projection operator, which we're about to use to go. But, you know, we always like to tie things in a neat bow when we're putting these knots together here. So we're talking about the scalar product that we have already looked at that has norm squared, where norm is the square root of the inverse integer that comes out from dividing L0 by order of group. Okay, so that's the norm that will get us. Now the left action is this, and this is very similar to something that's and we're rushing a little bit putting this together, so a lot of the links for this are, and this is mostly my fault, pointing in wrong directions. So we will this afternoon get that squared away. But anyway, this is the matrix that I talked about, the irreducible representation written in Dirac notation. And then, here's what happens when you apply a local G to this. The local G goes up and knocks on the door of the projection operator for that state, mu m n. Okay, hey, can I come in? And the projection operator says, who are you? You're an alien. And being a liberal alien, he says, come right in. That's the Mach-Mach condition right there, the commutation condition right there. And then here's the Mach-Mach inverse right here. When this guy, the alien, the guy that's from the inside of the molecule, right, runs into 1, okay, he turns into an operator that this guy knows. He turns it, inserts that operator. This only works for the 1 states, you see. It's only true. G bar is not equal to G blue inverse. This is global. This is local. They're not equal to it. Far from it. They're intertwining. Okay? But for this state, they do the same thing. Okay? So that lets us have a formula to go along with that one. Now I've got to do a sum over the d of G inverse, because G inverse does hit the left-hand side of that thing and give me a sum. Okay? And that sum is over the projection operators. It'll be a sum over the body quantum numbers, the n's, the things that are on the right-hand side of this projection operator. Okay. So instead of what we had here, we get that. Very similar. It's a G inverse, and it's a sum over n's, not m's. Okay? So there's your local G matrix component. There's your global G matrix component. Pretty much the same, except for this one using the red indices, the n's. Okay? Pretty much the same. Oh, yes, the prime is on the left, the unprimed is on the right, but this one's conjugated. It's a complex conjugate, if it happens to be complex. Not a worry for us, we picked a representation was totally real. So that is not going to be an issue here. But if we pick C3, you got to be careful. Okay. All right, I think we're in business here to go ahead and do the, I guess it's pièce de résistance for this whole theory of global versus local. What we're going to do is we're going to be dealing with matrices that first are block diagonal. That is, this is the typical projection operator base ordering, where I go XX, YX, then XY, YY. Do that order. Not the flip, the one that gives me blocks on the diagonal. That's a typical global view of the irreducible representation coming out of the regular representation. Flip that guy, and you smear them all over here. But each one's a unit matrix times a coefficient, you see. Very different from this one, which are not unit matrices at all. Okay. And you see the local G bar matrix not connected. You see, they're all sort of not concentrated, I would say, not close to the diagonal. All right. Now you can do this another way. You can go ahead and flip this one, get a global matrix that's not concentrated on the diagonal, and while you're at it, you might as well flip that one, and then the stuff that goes with the global will be on the diagonal. Of course, they're all conjugated because that's what the matrix elements give. So here's four really possibilities for making matrices that would be various kinds of Hamiltonians. We're going to stick with pretty much just one. So we're going to have an H matrix in the G basis with all the parameters, okay? All 6 of them, 1, 2, 3, 4, 5, 6 different parameters, but then it's got symmetry, so those parameters show up as the same parameters reordered. And it turns out we're going to write the formula just in terms of things that are in the top row, because all the other rows have nothing new to offer to us. That's the whole point of a symmetry. Okay? So we're going to figure out what these numbers are. And basically we only have 1, 2, 3, 4, 5, 6 different numbers, because this one is equal to this one. And that has to be, because the character table told us that the E representation, the E had 2 of degeneracy, twofold degeneracy, right? So whatever we get can be something that's not diagonal at all, maybe. Okay, but this has to be the same. Has to follow this one. The eigenvalues of this have to be the same as the eigenvalues of this. That's a rule of symmetry that everyone knows. But this one is telling us, if we didn't get it when we did the first run through on this, that pretty well shows that you've got the degeneracy that you need. So we're going to go ahead here and do it with a norm for a while. But I want you to notice something at the end here, is the norm completely cancels out. This thing cancels out. It comes once one this way and then comes inverted, and it's out of here. So I write here in New Yorkese, which I don't speak fluently, because I've only been there short times, but forget about it, right? That's what they say, forget about it. Whenever they want you to not think about something, right? Forget about it. Okay, so I say, yeah, this is important for some things, but this thing is going to avoid that altogether. They'll cancel. So that's an important part of this thing. So here we go. This is the thing that we're doing. We're calculating the matrix element of this H matrix, basically, this clumsy thing here, with projection operator eigenvectors. Okay? We've got an MA here, and we got an NB here. These are the local things that make us have a local matrix. Okay? Now, what I can do is I can take that projection operator symbol out of the bra, but when I do that, I've got to turn that MA around to AM. Now this one, I take it out and it's in the right order, but this is a conjugate, you see, and the conjugate of AM is MA for all of these projectors. That's an interesting thing. So that is what we are dealing with here. We got and the red letters are components of a local body quantum or quantities. Okay, so there'll be a norm squared here, but that norm squared is going to get canceled. That's what's basically happening here. And so here I do the Mach-Mach commutation. Okay, the Hamiltonian here being made of local stuff can have the projection operator go right through it like that. Okay, and then what happens is the m's and m's have to be equal. That's just the multiplication of the p's. All right. So we get a little delta function out here that tells us don't bother using projectors with different global indices. They're not going to give you anything. So here we go. We got an h times a projection operator times 1. Then we go ahead. This is the orthonormality. We go ahead and expand the projection operator. But what happens is the norm squared is LL over G. So cancels. Gone. This is really a cool formula. You see what's happening here? Each of these is one of these numbers in the top row. Okay? And then it's just the wave function right here. D star, AB. Completely, I've lost all those coefficients that make it be a norm. Who cares about norms? We're getting the answer directly in terms of these 6 numbers. That's really cool. That's you got to admit there's something neat about playing local global here. So basically, we're going to be summing over R sub, if you were to call all of these things R's, but we're not. We're calling them by the names of the group elements that label the position of each of the 6 places that exist in this D3 problem. Okay? So let's go ahead and put in some numbers. Let's try alpha, the representation, to be A1. Well, A1's a scalar, so all you're going to get is a bunch of dA1s, and that's just 1. So all you're going to get from that is the sum of the top row. Now, we are at this point using something that we know just from the time reversal, is that we're going to require that this is a complex conjugate of that. So we're going to have R2 be R1 complex conjugate. But aside from that, that's the first answer from our things. We have now gotten this value right here. Okay? Done. All right? Next stop. Well, now it's going to be these representations. And if you look at the character table, you don't even have to look at the representations, but the last 3 are minus. So this one's going to be the same numbers summed up, but with the last 3 with a minus sign. Okay? Now it starts to get funny. Okay? Because now we're going to use the XX component. That's the first diagonal component of the E representation. Okay? So I got a 1 here. Okay. Now, let's see, how did that become a, well, because I've decided to divide by 2 so that I wouldn't have fractions here, that's a 2. But that would have been a 1, and then these would all be a halves with minus signs corresponding to these numbers right here. And then the last one, the I3, gets to be twice as big with a plus sign, just like the first one. Okay? So, we're up to the point now where we have this number, and we've gotten this one. Now we've got to start playing a serious thing here. The next stop here is XY. Okay. Now this is a Hermitian operator, presumably, so if we get XY, we probably have YX as well. Especially since we're dealing with real numbers, then that would definitely be the case. So here we go with the xy component now, and we're pulling that off. 0 there, square root of 3 with a minus sign, plus square root of 3, minus square root of 3, plus square root of 3, all over 2. That's giving us that little collection there. And then we go ahead and jump to the last one, because if this is Hermitian, we're going to get yx be equal to xy complex conjugated. If that's not true, if it's a scattering matrix, you've got another number here you've got to write down. But if it's a Hamiltonian, that's your answer. Okay? Now let's discuss this, because the whole point of this was to have some local symmetry. We picked as our golden boy, okay, our whatever, our king, I3, right? I3, out of all of these, counting the unit operator, was going to be a diagonal operator, okay? The I3 operator is going to be diagonal, okay? And indeed, back up here and look, yes it is, okay? It's a C2 subgroup. So, the question is then, what else does this tell us? In other words, what does it take for me to get this to be a diagonal matrix? I've got this coupling right here, you see. And at this point, you see, this becomes one of those A, B, C, D matrices, right? That's A, that's D, that's C, and that's minus C, and you add in actually I times C and with a minus sign, and I times C with a plus sign. And then there's a B. So just take that thing, it's a Hermitian matrix, so it will fit on an A, B, C, D numbering system of some kind. But with this symmetry, if we're really demanding that we have the I3 symmetry, then I'd better have I1 equal to I2. That will kill that, right? Then I'd better have the complex conjugate of R1 be equal to R1, so it kills that one, right? So if that's the case, and that's reasonable for having set I3 as a thing, I'm not going to be allowing it to do moving waves. I'm going to be getting 2 standing waves with different eigenvalues when I do that. So that's kind of summed up over here where I write them out as they appear, but here is what it would be if I choose, you see, local constraints. R1 equal R1 star equal R2. If I choose that, I'm still good. I can do that and still get a diagonal matrix. And these are now the eigenvalues with that constraint. And you see what it's boiled us down to is we've boiled it down to the point where the number of parameters, and remember, don't forget about, we've got these 2 numbers right here that we got immediately, right? That was just like abelian group theory there. But these, that makes 4 distinct numbers. So we really have 4, it's a 4-parameter problem, and that's all you can have and get a diagonal thing, because this is a symmetry of rank 4. You can do it a lot of different ways, but to actually get a diagonal matrix and have that symmetry, it's 4 numbers. 4 different numbers are playing there. So that makes this an orthocomplete eigensolution. That is, you give me the data, in other words, you tell me I found this A1 at that energy, and I found this A2 at that energy, and this guy here, and this guy, and so on, the E's, the 2 E1 and E2s, I found at them, I can solve you for your tunneling parameters and be exact. You can reverse engineer. And that's something that group theory problems are usually not known for. That's what this global local gives us that you don't find anywhere else, as far as I can tell. I mean, they go and just throw a thing on a computer and not worry about it. That's a typical approach. But here you have the possibility to get an analytic result that goes forwards and backwards. Okay. That's what this says here. Local symmetry determines all levels and eigenvectors with 4 real parameters. That's a tall order, but the symmetry made it possible. Now you can ask what happens if I let some of the group parameters turn on, right? Break the symmetry. We have not explored that yet. There's a lot of possibilities there, so that's something to look at. This is another statement of it that just sort of sums it up with the matrices that so those are the eigenstates. Now, with this, and I guess it's a little out of time, but we are running some of the waves on the far screen there that we get by this, and we've already discussed what it meant to be totally anti-symmetric in global and local, totally symmetric in both global and local. You see, it's globally symmetric there. This is the same as that, and this thing is reflection plane. You just look at that. So is it this way and every way you can think of, a scalar. Then this is a pseudo-scalar. It gives you a minus sign every time you do the operation I3, for example, either internally or externally. It will give you a minus. But these guys give you both. This one right here gives you both symmetry and anti-symmetry. This one right here gives you 2 of them that are, I'm sorry, this one right here is just like this one. 2 of them are symmetric. But this one is symmetric and asymmetric. I should say anti in the global and symmetric in the local. This is the opposite. Symmetric in the global being a reflection that takes that into that. But inside that box there, it's anti-symmetric. Well, when you have them combined, then it makes it impossible to have a wave function here. You can't do both. So, nothing there, nothing there. That I mentioned last time. And you see in an actual simulation, it knows nothing about group theory, it just knows what the shape of this potential is. It still managed to sneak a little bit in there, but that's because we break the, we let it see a little bit of its global outside stuff, and it manages to get a slight wave function there. This one, pretty dead there. So these are the 2 that would have nothing in the middle well of the triangular tunneling arrangement that this is. So the clash between those 2 reduces the wave function in a real situation and even makes it 0 when you're really deep, when you're really feeling the locality of this potential. Now you start climbing up on top of the potential, goodbye Columbus, as they used to say in the movies, right? We're out of here. We're not paying any attention to the local town. But goodbye Fayetteville, right? I'm a global citizen now, right? As soon as I start climbing out of here. So that's what's starting to happen right here. It doesn't happen just as you get to the top of the well. It grows exponentially.
Where's my airplane?
Where's my airplane, right? Where's my yacht? Now, we're going to be doing the same thing with vibrations. Now global and local symmetry is very obvious. That's local and global, right? They're all the same, okay? But they're also reflection symmetric. This guy's perpendicular. That's anti-symmetric with respect to turning around that horizontal plane or axis, okay? Then here are the guys that are both, and they have no motion going on at the clash points. And then here's the case where it's totally symmetric, but not trivially so. And this one's totally anti-symmetric and not trivially so, as is this one. So we're going to be talking about that. What it does is suggests that the way to handle force fields is to imagine springs that are curved. And you can make some springs that will make it sure that the I3 symmetry is a symmetry, internally as well as externally. So we haven't explored this very much. but there's a possibility that this might be a better way to fit the vibrational frequencies of some pretty squirrely molecules, not the least of which is our old friend right here. Okay. So just putting springs directly from atom to atom